Welcome everyone, and in this lecture, we'll continue the lecture 2 of Design and Analysis of Algorithms. In the last lecture, we started stable matching problem. We defined the problem, where in the problem, we are given n men and n women, as it is, and each man has their own preference list. Women also have their own preference list, and our goal is to find a stable matching. Everyone is matched, it's a perfect matching, and there is no stability in the sense if there are two matching edges, then there are no two cases like S and R in this case, where S prefers R over its current partner P, or R prefers S over its current partner A. So this is a notion of instability. So there is no instability and it's a perfect matching. That's what we're looking for. And then we saw several cases that it was not clear whether it always exists such a stable matching, and then how to find it efficient. We went via 4 examples in Bollywood movies. Sometimes we saw there is only one stable matching, and sometimes we saw there are two stable matchings. But in all cases, we found there is at least one stable matching. Is it only a coincidence or is it always true? That we don't know yet. And then we tried several heuristics. First one was local search, and we went to an infinite loop. And then we started with the greedy, which did not work. And then we proposed a modification, and the claim was this should work. And actually, this cute modification where each man is proposing a woman, and then they get engaged if the woman is available, and later it can be even broken. This was a Nobel-prize winning idea. So this algorithm that we'll talk about, it's called Deferred Acceptance, proposed by David Gale and Lloyd-Shapley. And Shapley and Alvin Roth, they won Nobel Prize for this work on stable allocation in 2012, the prize in economic sciences. Unfortunately, David Gale died in 2008. Otherwise, he could have been also one of the Nobel Prize recipients. The reason I chose this to be the first algorithm of the course is also to highlight algorithmic thinking. And this is from the original paper, College Admission and the Stability of Marriage by Gale and Shapley. And they wrote this paragraph. Let me read this. Most mathematicians at one time or another have probably found themselves in the position of trying to refute the notion that they are people with a head for figures or that they know a lot of formulas. In such times, it may be convenient to have an illustration at hand to show that mathematics need not be concerned with figures, either numerical or geometrical. For this purpose, we recommend our theorem. The argument is carried out in not mathematical symbols, but in ordinary English. There is no technical terms, no knowledge of calculus is needed. One hardly needs to know how to count. Yet, any mathematician will immediately recognize the argument as mathematical, while people without mathematical training, they will find difficulty in following the argument. So it's one of those algorithms from book which solves a very important problem, but it's very simple and elegant. So we'll see the algorithm. Let us start with the algorithm. In the beginning, we initialize all men M in M and W in W to be free. And then our goal is to match everyone. So there is a while loop. While there is a free man M and he has not proposed to every woman, we'll run this loop. Now it's not clear if the loop is infinite or not, but as long as there is a free man, we will run this loop. And we have to prove that at the end of this loop, it will terminate. So if in the loop, what we do first, M proposed to W, the highest ranked woman in M's preference list to whom W has not yet proposed. So M will propose according to his preference list, and the women can accept or reject. Now, whoever women have rejected, he will not propose again, but he will propose the highest ranked woman to whom he has not proposed yet. So each proposal is a new proposal. And if W is free, then MW gets engaged, because at that point, W has not received any proposal. Otherwise, W would have already been engaged with someone. So if she's free, this is probably good. She will get engaged. Otherwise, if W is already engaged to some other man M prime, then there are two cases. If W prefers her current partner M prime over this new proposal M, then M will remain free and W will continue with M prime. But if W prefers M, the new proposal, over her current partner M prime, then M prime and W edge will be broken, M prime becomes free and MW becomes engaged. And this loop continues. So in each round, at least one man is proposing to one woman, and it's a unique proposal. This proposal is not repeated. And at the end, we return the set of all engaged pairs. So let's look at this example. So we have Bernie, Marshall, and Ted, and they have their preferences. And similarly, Robin, Lily, and Christian, denoted by R, L, C, and B, M, T, and their preferences. Now let's match. So let's say the main proposes. Bernie first proposed to Christian, and she is available now. So this will be a match. They will get engaged. Then Marshall comes, he is free. His first preference is Robin. So he will propose to Robin. Again, Robin was available, so she gets matched to Marshall, engaged. And last, Ted comes, his preference was Lily. So he will again propose. And as all were available, so all three gets engaged. And then there are no more free men. So this is a stable matching, will stop. And we can find out it's a stable matching because all Bernie, Marshall, and Tate, they are proposing to their highest ranked women. So they are getting the top preferences, so it's stable. On the other hand, if we run the same algorithm, but now instead of men, let's say women are proposing. We start the algorithm from the beginning. So then Robin will propose to Bernie. Her first preference, it will be matched. And Lily will propose to Marshall. Her preference, it will be again matched. And then again, Christian will propose to Ted. And then again, it's matched. In this case, again, all women are getting their top preferences, and this is stable. So you already saw this case in the last video, where we saw there are three stable matchings at least we saw in this situation. In one case, men are getting best preferences. In one case, women are getting best preferences. And the other case was when everyone was getting their second preferences, which was also stable. So in the algorithm, we saw that even if we change the order, for example, instead of Bernie proposing first, but first Marshall proposes and then Tate and then Bernie, we'll get the same matching for men. So if men proposes in any order, we'll see they're getting the same matching for this instance. Is it always true? That's not clear. And then for women also, if women propose, we are getting a different stable matching, green. But again, women, if we change the ordering, we still get the same matching. And we are not getting the third stable matching where everyone is getting the third matching. So what kind of stable matchings we are getting from the algorithm, that we have to study. But before we go there, first the basic property. Why does this algorithm always terminate? And do we always return a perfect matching? Before going to the stability portion, these two are even not clear. So there are two properties we see in the algorithm. So whenever we are analyzing an algorithm, first we spend some time analyzing the properties of the algorithm. The first property is W remains engaged from the point at which she receives the first proposal. So once she receives the first proposal, that is the best one she has, and she will accept that and she will engage. And later, she will only break it if she gets a better proposal. So sequence of engagement gets better for her. And M, he will propose according to his preference list. So sequence of women to whom M proposes will get worse and worse. Now, let's look at the runtime. To analyze the runtime, we need to somehow measure the progress, that we are making some progress in each round. There should be some parameter which increases strictly in each iteration. So let's say consider number of free individuals or number of engaged pairs. Are they increasing in each round? No. For example, if let's say MW are matched and then some proposal M prime comes for W and W prefers M prime over its current partner M, then M gets free and M prime gets engaged. So number of free individuals remains same. One person becomes engaged, but other person becomes free. Similarly, number of engaged pairs also becomes same. The third proposition is, let's consider each iteration, and as we mentioned earlier, each iteration has a unique proposal. A man will propose to a woman and the woman rejects. If it rejects, then it will not propose to that same woman again. So each proposal is unique, and So each iteration will have some man proposing for the first time, and it's also the only time, to a woman whom he has never proposed before. If we consider PT, which is set of pairs MW, such that M has proposed W in some iteration 1 to T, then clearly this is increasing. Each round is a unique new proposal, new MW pair which is appearing. So PT plus 1 is strictly more than PT. Now, what is the maximum size of PT? The number of edges, which is, it's a KNN, it's a complete bipartite graph at mod n square. So it should not be more than n square. In fact, we can show that there are instances for which you need omega of n square amount of steps. So it's almost tight analysis, but it will stop within n square iterations for sure. Okay, so it will terminate. That's the theorem. So we'll also call it GS or Gale-Shapley algorithm, as well as Deferred Acceptance Algorithm. It terminates after n square iterations. Now what we have to show, it's also stable matching. So there is first perfect matching, and second, there is no stability. So let me write down the proof. So to prove it, what we'll do is, there are several ways to prove a theorem. We can try induction, we can try contrapositivity. In this particular case, we'll use contradiction. Let's try. For contradiction, assume, the reason I'm writing is, normally in class I always use Blackboard because it takes time for the brain to understand the algorithm. But here, as it is YouTube video, you can pause anytime and go back, rewind, and go over what I have taught. But for the proofs, I will still write down some things. So for contradiction, we assume that there is a free man at the end, or then at some point of time, and maybe at free man, and all women are matched. So number of matched women is n, but it's a matching. So every woman will get matched to a unique man, a different man. So number of matched men is also exactly equal to n. So that means number of free men is total number of men minus matched men, which is 0. And that's a contradiction because we assumed there is a free man. So all men will be matched at the end. This is a perfect matching. Now, second property we'll show is no instability. Same. We assume that for contradiction, assume there are pairs written by our algorithm MW and M prime W prime such that M prefers its instability. So M prefers W prime over its current partner, which is W, and W prime prefers M over its current partner M prime. So in the figure it will look like this. This is the matching. M, this is W, this is M prime and W prime. And we are seeing M is preferring W prime. This one is his first preference, and W2 is second preference. For W prime also, we have first preference as M and second preference as M prime. Now, let's look at the algorithm. So, add one more page. So now let's look at the algorithm. What we have from the algorithm is in Gale-Shapley algorithm, M's last proposal was W. If you remember, the way algorithm works is M will propose according to his order of preference, and as W was matched at the end, it will not propose after W. So W was the last preference, last proposal in the algorithm. Now, as we are assuming here that M prefers W prime over W, so M must have proposed W prime before W, but then it was not matched with W prime. That means W had preferred, and then W had preferred some other person, M double prime, over M. That's why M was not matched with W prime. And at the end, W prime is matched with M prime. And the choice gets better and better for women. So W prime prefers final match M prime over M double prime. That's why there was a final match. It will only get better. Or it could also be the case that M prime equal to M double prime. But in both the cases, then we are getting that W prime prefers M prime over M double prime, and W prime prefers M double prime over M. So that means W prime prefers M prime over M. Now, if we look at this statement, W prime prefers M prime over M, and look at these statements that W prime prefers M over M prime, there's a contradiction. So it is not true. That means we'll have no instability in this algorithm. So quite simple algorithm explanation. There is no math, just sequence of logical argument, which shows you'll always end up with a perfect matching without any instability, which is a stable matching. So the algorithm is correct. Maybe you can pause the video for a couple of minutes and understand this. Now, this is not the only surprising property. There are many more interesting properties of this algorithm. So there are, I think, multiple stable matchings which are possible. But what kind of matchings are written by the algorithm? And if we have different execution order, does it lead to different matching, for example? Now, what is interesting is, in this case, every man always ends up with the best possible partner under stability. And each woman also ends up with the worst possible partner under stability. So let us formally define what I mean. So there are several stable matchings. W is a valid partner of M if there is some stable matching where M and W pair. And among all of them, best M is the valid partner of M, and no woman who M ranks higher is a valid partner of M. In the sense, let's say there's a person M, and he has multiple ordering like W1, W2, W3, W4. Now let's say there is no stable matching where W1 appears as a partner of M, but maybe W2 appears. But again, no W3 appears in any of the stable matching with M, but maybe W4 appears. In that case, both W2 and M4 are its valid partners. And among these two, what is the best valid partner or best M is W2. So there are no women who M ranks higher is a valid partner. So though W1 is higher than W2, W1 is not a valid partner. In this case, W2 is a valid partner. And what we are saying that W1 anyway, if M gets W1, then it is not stable because it's not part of any stable matching. But among all possible stable matching, whatever is the best possible partner it can get, it will always get that partner. So let's go over one example. So in this case, we have M1, M2, M3, three pairs, and W1, W2, W3, and this is the preference W1, W2, W3, etc. Now, if you look at the top partner, M1's top preference is W1, M2's W1, and M3's W2. This is the top preference. But are these best valid partner? So let's run the algorithm and see what kind of solution it returns. So maybe first M1 proposes, its first preference is W1, so M1 will propose to W1. Will W1. And now M2 comes. M2's first preference is also W1, so M2 proposes again to W1. And at this point, W1 prefers M2 over M1. So this bond will be broken and M2 and W1 gets matched. Now M3 comes. M3's first preference is W2, so M3 proposes to W2 and it gets matched with W2. Now M1 comes and M1 proposes to W2, its second preference, where W1 has already rejected, so it can only propose to W2. And at this point, W2 finds M1 is preferred over M3. So W2 will break the pairing with M3. Now again M3 is free, so he will again propose, as W2 has rejected, it will propose to W3. Sorry, W1, because after W1, its preference was, after W2, its preference was W1. So M3 proposes to W1, and W1 again finds it prefers M3 over M2, its current match. So again, M2 and W1 is broken, M3 and W1 match is created. Now M2 comes again, M2 proposes to now W3 because others have rejected. So M2 proposes to W3 and now all are matched. Now we see that M1 is getting W2, its second preference, M2 is getting W3, its third preference, and M3 is getting W1, its second preference. So none of the men actually are getting their top preferences in this example. In fact, M2 is getting its worst preference. But the point what we are saying in this algorithm will, if M2 is getting W3, that means other two, W2 and W1, which are ranked higher, are not its valid partners. So in no stable matching, M2 can get W1 and W2. The best possible matching, best possible partner one can get in a stable matching for M2 is only W3. So we'll prove this theorem that every execution of the algorithm will result in a same set where M is matched with its best valid partner. So it's very surprising that why can't two men have same valid partner? Everyone has to be distinct, otherwise it's not a matching. And why it gives the best possible outcome for every man. So earlier we saw examples where either men were happy or women are happy. So that we had to make a compromise. But once we make that compromise, this is ensuring that all men are happy simultaneously by the algorithm under stability. And also why order of proposals has no effect on the final outcome. It's very interesting properties. So we'll try to again prove this theorem. So proof. So we'll again use contradiction. So for contradiction, assume first time or first instance when some M is rejected by its valid partner W. So in the algorithm, men are proposing one by one, and the first time M is rejected by its valid partner W, we look at that instance. Now, in this case, W is also the best valid partner because the rejections are according to the order of preference. So the first valid partner that we reject is also best valid partner. And we want to show there's a contradiction. If we show, then we're done. So how do we show? So if M was rejected by W, then W must prefer some other man M prime over M. That's why it did not choose W, it rejected. Now let's look at M, W, and M prime. So as W was a valid partner, that means there is some matching, some stable matching, where the matching is like this. So M is matched with W, and let's in that matching, M prime was matched with W prime. Okay. And what we are saying now is W prime prefers M prime over M. Now let's look at this example. So in this case, there is some stable matching with M W and M prime W prime pairs. Now what can happen that if W prime prefers, sorry, we're talking about M. So if M prime prefers W prime over W, then what is happening is the W prime was matched with M prime. It's a valid partner, and M prime is preferring W prime over W. So in the proposal order, M prime will propose to W prime first, and then if W prime rejects, then only it will propose to W. So in the algorithm, as W was preferring M prime over M, that means W prime cannot be preferred over W for M prime. Because otherwise, if M prime prefers W prime over W, then the only way to reach W is if W prime rejects M prime. But W prime will reject M prime. That will lead to the first instance when a man, M prime, is rejected by its valid partner W prime. That's a contradiction because we assume that the first time when some man was rejected by its valid partner W uh, was W. So my point is M prime W prime appears before MW in the iteration, and we are saying this is the first time the proposal was rejected by a valid partner. But then this cannot be a valid partner. So W prime, if it was already preferred over W, then there will be rejection. So that's not possible. So M prime prefers W over W prime. But then what happens? M prime prefers W, it's the first preference, over W prime. That's an instability. Because now W and M prime prefer each other over their current pairing in the matching. But we saw that in the matching written by the algorithm, there is no instability. It's a stable matching, which is a contradiction. So we proved that the algorithm always returns this pair where a man is matched with its best partner, best valid partner. Now there are several variants. What's interesting is instead of bipartite graph, if you go for general graphs, let's say there are 2n people and it's a roommate problem. And I ask that, okay, there are ordering of all 2n minus 1 people, and then can we find a stable pairing? And that may not exist. So one example is this case, A, B, C, D, and this is the numbering which shows their preference. Now let's say I have a pairing like A, B, and C, D. In this case, we'll see that B prefers C, which is first preference, over A, its current partner, and C prefers B over D, its current partner. So it's not a stable matching. And other two cases, there are 6 edges in this case. There are 3 possible matchings, and we can show none of them are stable. All are unstable. The beauty of Gale-Shapley is also it can actually generalize to a lot of other cases, not the general graph, but let's say you're matching residents to hospital, which was mentioned in the original title. Now, sometimes it may not be complete list, only some partial list. Some participants might declare, okay, some hospitals are unacceptable. So in this case, one side is hospital, other side is doctors. There can be unequal number of men and women. There can be limited polygamy. So some hospitals might want to hire multiple doctors and so on. In this case, there is an algorithm which needs a bit of centralization, unlike the previous algorithm where a man can decide what to do. Here, the algorithm says that in kth round, you take all unassigned doctors and kth hospital in their priority list because others will already be rejected. And then hospitals are assigned to doctors based on hospital's priority over doctors. So this is a generalization of the previous deferred acceptance algorithm. So maybe pause for a couple of minutes here and try to understand the algorithm. And if you're interested to know about this, I'll mention some references. There are a lot of other interesting questions like commutatorial question. For example, how many possible stable matchings are there? The upper bound, the trivial upper bound is n factorial. If there are n men and n women, for the first man, the number of perfect matchings, let's say n factorial, because first man can choose any of these n people. For a choice of that, we can choose second man can choose n minus 1 women. Third man then can choose n minus 2. If you multiply, we get n factorial. What is the trivial upper bound? So we already had this tile example where there was k22 and there were two stable matchings. And similarly, if we if we have n, k, and n case, we can break the graph into n by 2 pairs of k22. And for each of them, we have two stable matching. So we get 2 times 2 times up to n by 2, 2 to the power n by 2. And then there is some improvement, of course. The lower bound was improved by Donald Knuth using an instance of Irving and Leather from in 1970s to 2 to the 2.28 to the power n, which is still the best one, almost 40 years. On the upper bound side, there is progress, and the best known bound is 3.55 to the power n plus some constant by Palmer and Palvogi from Fox 21. This is the state-of-the-art situation for the problem, and Fox is the top theoretical computer science conference. It's called Foundation of Computer Science. So if you're interested to know about more, you can check this paper. So for this problem, I followed Kleinberg-Tardos chapter 1, but you can also read from CLRS 4th edition chapter 25.2 or Jeff Erickson's chapter 4.5. This problem, there are a lot of programming exercise. For example, CodeChef or SPOJ has problems like stable marriage. If you're interested to write a code, write your code and test. There are advanced materials. There is a book by Donald Knuth on stable marriage problem, also by Gusfield and Irving. There is a course taught by Prajakta Timurkar from CMI on matchings under preferences, which also lists many recent progress and nice open problems. So this lead to the end of this lecture. So what we learned about stable matching is summarized by this cartoon, that men should propose early and often. The algorithm says once a man is matched to its best valid partner, then it will not break that bond. So you have to reach your best valid partner as soon as possible. So you have to propose multiple times, because you'll be rejected by the top preferences, and then only you'll reach the best valid partner. And also we saw the algorithm is good for men. They are getting best valid partner. For women, it's worst valid partner. So one who is proposing, they are having more advantage. So women should ask out guys, they should propose, and then they will get advantage. And third thing we realized is CS folks should know algorithms, and it will help them to get best partners. So this ends stable matching problem. In the next lecture, we'll talk about greedy algorithms. Thank you.